Greetings. Welcome to the first computer musing of the fall quarter. I'm glad to be here in Skilling Auditorium again after, I don't know, I taught so many classes here in the 70s, and this is a great building, but not as easy to get to as if it was in my office as I used to. Anyway, here we are, and it's a nice place. And today, you might be able to see from the display on that we're celebrating the publication of a book called "Selected Papers on Discrete Mathematics." Sean, can you get a picture of all these books that are sitting up here? Yeah. This is. As you know, when somebody publishes a book, he's supposed to go and give a book tour. And so today is the beginning and end of my book tour. Welcome to the book tour for this book. You know, I don't have time for a longer one because I'm writing another book. But anyway, here it is, and this means that you guys get a chance to get an autographed copy if you you happen to have enough in your wallet at the moment. I don't even know how much it costs. Let's not worry about that. But yeah, it's cheap. Yeah, no, it's inexpensive. Well, anyway. I mean, when I was a college student, Mad Magazine was unique because it was inexpensive and also cheap. What was I going to say? Anyway, it's starting a couple of weeks ago. I started getting letters from people who had their orders shipped from Amazon.com. So it's kind of a new book, and maybe the longest book I ever wrote. I mean, it's a little hefty. It ends up at page 812. I'm going to tell you something about this book today, but my main topic is notation, announced because really that's one of the most important themes in the entire book. And all my life I've wanted to give a lecture about notation. It's a key thing to me, and so today is my chance. It's the greatest time. I've been looking forward to this for I don't know how many, 65 years maybe, I don't know. And I hope I can pull it off. Now, let's see, what else should I say before I get going? Yeah, I'm pleased to announce that the Stanford Center for Professional Development has just decided that they will archive all the computer musing lectures and including as many of the old tapes as we could find, and about a dozen of them are already on the internet. And if you go to my news page, there's a way to click, or you can go directly to Stanford Center for Professional Development and search for Knuth. You'll get referred to these, to the ones that are online now. And in the next weeks, we're going to have more and more online, including a few of the classes that I taught in the past, like one of the problem-solving seminars that we had, class on technical writing. More and more of these things are going to be stored in webcast form, so that your children will be able to watch the lecture I'm giving today, and maybe your grandchildren. So if you ask a question, you could identify yourself, and your grandkids would be able to experience hearing this question. Yeah. Susan, right? Perfect. She just has a new granddaughter. Okay. So now another thing I wanted to say before because people are still trying to find this room, is you might notice that there's a whole bunch of paper on the floor. I don't know if Sean can pan on how easy is it for. Yeah, he can. Okay, so now I've been cleaning out my office, and when you write papers, one thing happens is that you get free reprints of the papers, and people aren't requesting reprints the way they used to be anymore. Although, as you'll see later today, the reprints are still kind of intriguing and nice artifacts. So what I did, anyway, in order to economize on the space I need in my office, I decided that I would reduce the number of extra reprints that I have, so that I only have 5 left of each paper. And this is all the excess sitting here. And these are freebies. If you don't take them now, they'll be thrown away. And so that's too bad, but there it is. That's for those of you who can't afford to buy this book. All you have to do is find the right 40 reprints in this pile here, and you can make your own. Okay. So it includes reprints of papers that aren't in this book too. This is volume 6 out of a set of 8 that are planned, so the first, well, I might as well go through the whole list. The first one was called Literate Programming. The second one was called Computer Science. Selected papers on computer science. The next one was called, what was it called? What?
Digital typography.
Digital typography, that's right. Everything about typesetting. And then the fourth one, Analysis of Algorithms. The fifth one is Computer Languages. I'm going to have the book tour for that in December at the Computer History Museum. And then this one, Discrete Mathematics. The other two is going to be called Design of Algorithms, and then the last one is called Fun and Games. And you'll find papers here about design of algorithms. For example, if your research topic happens to be what they now call the Knuth-Bendix algorithm, you can get a reprint here of the Knuth-Bendix paper that started that field. So anyway, there's a whole bunch of stuff here which I hope somebody will like, and you can always get a good price for it on eBay if nothing else. In 10 years, I mean, you have to find storage space in your own office, though. Now, okay, now notation. That's the thing that I think is key, and near the beginning of this chapter, this book I dedicated to my PhD advisor, Marshall Hall, and it includes my thesis work in here. 2 of the chapters are based on a thesis I wrote about finite projective geometry. In the middle of in the middle of this book, you'll be able to find these books on finite projective planes. But in the beginning, after a paper that I wrote with Marshall Hall, is this chapter 2 notes on notation, and this is something I want to talk about in the next few minutes. The paper has a kind of interesting history. When I started to write it, I wrote to the editor of the American Mathematical Monthly, who's my friend Herb Wilf, saying, would you mind if I wrote an article about notation? And, well, here's his letter. He says, Don, I would gladly sell my grandmother to get a paper by you for the monthly. I think he says this to everybody, but anyway, he's a lot of fun. I have some trepidation because the topic of mathematical notation is intrinsically about as exciting as IRS Form 6378. However, in your hands, I have every confidence that even that subject will be exciting. You may correctly surmise that I'd rather have one about mathematics. But from you, I'd take one on the sex life of the Antarctic Knuth. Anyway, that was his take. That was his response. But anyway, here you are to hear about notation, right? And in fact, this paper was the winner considered the best paper published in the monthly that year. So a lot of people did seem to like it in spite of this thing, and I left out about the Antarctic Knuth. Because I think other people agree with me that there's something important about the notations we use. Now, it's not for everybody. I think some mathematicians notation is completely pointless for them. I mean, someone like Poincaré probably wasn't at all fussy about notation. He had a different kind of vision. But me, I do my mathematics in a very manipulative fashion. I mean, I'm a manipulator, you have to admit. Namely, I see patterns in the formulas in front of me. To me, and he sees things, in 4 dimensions. Well, I've been having trouble with 2 dimensions, maybe 3 sometimes. But he's got, I don't have a really good geometric intuition. But algebraic, something, I was born with, and there are other people like me. For us, notation is really key, because if we don't have a good notation, then we miss the pattern that we're working on. Now, the way mathematics works in every case, including geometry, most effectively is that you take a problem and you can show that something is true if and only if something else is true, and so you can state your whatever you're working on and transform it into something that is equivalent to it but looks different, and then you can work. Then that might suggest insights that you wouldn't have seen in the original form of it. And this is so true in the case of algebraic approaches to stuff. You take a problem and you can't psych out the answer to the problem in your head. So you put the problem into symbols. And then you look at the symbols, and then you work on the symbols. You don't have to understand what the symbols mean. You just have to, what the symbols mean in terms of the original problem. You only have to know what symbols mean in terms of symbols and how to convert one formula into another one that's like it. And you work on this way, and you learn to trust the symbols. And then you can translate it back, and you've got an answer to your problem. Now, the better your notation, the better this technique works. And that's the way that's most comfortable for me. And when I started in 1970 teaching a class at Stanford called Concrete Mathematics, and I gave the class 15 times, and it's really I didn't want to call it that because it wasn't as catchy, but I could have called it how to manipulate formulas, because that's what the subtext is. Really learning how to see that if there's a formula that suggests simplifying it in a certain way, and then you can do powerful things that you wouldn't have been able to psych out yourself without the formula. And this book is really a manifesto of how I personally like to do mathematics, and so the notations are key to it. And after teaching it for that many years, I finally found that some notations were working really well that I wouldn't have even expected. And when this book came out, that was the occasion when I decided to write this paper for the Math Monthly about 2 of the things about notation in this book that really clicked. So I will, but let me first go to this book, Concrete Math, which starts out with a list of notations at the beginning, so we can see what some of the. Now, a lot of the notations, of course, are standard in all of mathematics, but some of them are more unusual if you look at all papers that are written in mathematics. So, okay, so first of all, you have to decide between. You can zoom in more, I guess, even if you want, Sean. Yeah. So there's different logarithms. And so if you say log, this is log base 10 in my book, and ln means natural log. You look at other people's papers; they'll use log for natural log. Maybe a lot of people, and so on. Some information theorists will use it for binary log. But then there's a nice idea by Ed Reingold in Illinois. For binary logarithm, it's base 2, so use a 2-letter word. LG. Okay, so there it is. And so and this occurs so often that you need to know which logarithm that you're doing. The notation was important. The next one is interesting. It's the floor of x and the ceiling of x. When I was in graduate school, there was no notation for ceiling of x. The ceiling of x is the first integer you come to if you start at x and go up. So the floor of x, everybody wrote with 2 brackets. This was the floor of x. This was the greatest integer less than or equal to x. But the least integer greater than or equal to x, there was no convention. In fact, the people in Russia wrote this. It was definitely a losing notation. But that was some famous professor did it there, and so you had to follow. But it was. But then Ken Iverson, at the beginning of the '60s, decided, well, we could just take half a bracket. If you're going down, use the bottom half. If you're going up, use the top half. And he said, let's call this the floor and the ceiling. He made up those words as well. So I used that in the first edition of my book, Volume 1, and his idea caught on like wildfire. Within 5 years, 4 or 5 years, everybody in all mathematics was using these notations and not explaining. By this time you assumed that the reader knew what it meant. Well, maybe it took 10 years in some branches of mathematics, but it was this was a case, the most rapid transformation I know of any notation where it was picked up everywhere because there was such a need for it, and because these operations are dual. So many problems were more natural to state in terms of ceiling than floor, and then there's also to take the negative of the floor is equal to the ceiling of the negative. And vice versa, you can change floors and ceilings. It's easy to do operations on these symbols, and there's this nice duality relation between them. Okay, so another notation computer scientists needed was for a remainder. If you take one number and the remainder after division of x by y, this has slowly been catching on. That mod is now a binary operation instead of something that you only can use in parentheses off to the side when you're talking about congruences. I guess I want to talk. Yeah, I want to show you this falling factorial power thing here. Now this is a notation that is not spreading as fast as the other ones, but people need a notation. If you start talking about finite mathematics instead of infinite mathematics, you often find that you want to have the product not of x times x times x over and over again, but you want the product of n things in a row, starting with x and ending with x minus n plus 1. And this is called the falling factorial power. And then in other problems, you find that you need with the plus signs, you need to start at x and start going up. X plus n minus 1. Now, the reason is that in calculus, we have the derivative of x, which is d of f of x is equal to f of x plus dx minus f of x divided by dx, and then we let dx get infinitesimally small. But when we're doing discrete mathematics, we can't let dx get infinitesimally small. So we let dx equal 1. And that's called delta of f of x, which is f of x plus 1 minus f of x divided by 1. And the point is that the derivative of x to the n is equal to n times x to the n minus 1, but the delta of x to the n falling factorial is equal to n times n to the x to the n minus 1 falling factorial. Easy to check this. So when you're working on discrete problems, you need the natural thing for simplifying formulas is the falling factorial power. And so a lot of your intuitions of calculus go right through once you convert over to this kind of power, and then the rising factorial powers occur also. But some mathematicians only work with the falling powers, and some only work with the rising. They never had a problem. It's just like but for the same reason that we needed floor and ceiling both, in my books I definitely need both of these things, and so I decided, okay, I'm going to use the x to the n and put an underline in. I forgot to tell you that I was doing that, yeah, and the x to the n with an overline, is the case where they're running up instead of down. Now, other people use many other notations, and depending on which book you pick up, some people will write X with an N like this. Some will call X with a parenthesis N like that. Sometimes, lots of other combinations with brackets and other things. And half of the authors mean falling factorial by this notation. Half of them mean rising factorial by this notation. It just depends on which community they come from. And the people who use this notation actually is the funniest thing is they call this Pachhammer symbol, and they use it to mean the rising factorial. But Pachhammer used this notation to stand for the binomial coefficient, which is a falling factorial with an extra factorial factor. I mean, Pachhammer, never invented Pachhammer's symbol is the scandal there. But anyway, this notation is unambiguous. Nobody's been using this to mean rising factorial. Nobody's been using this to mean falling factorial. So to my great delight, earlier this year, after I see Percy in the back row, Percy referred me to a paper by Jim Pittman at Berkeley, and Pittman referred me to a paper by a man named Letterio Toscano in 1939. And this is a very obscure journal. In fact, the only library in California that carries this journal, the Commentationes Pontifica Academica Scientiarum, was the University of Santa Clara. And when I wrote to Jerry Alexanderson, who's the chair of mathematics there, saying, "Can you find this in your library?" He went to the library and found that this book was marked to be deleted from the library because it hadn't been checked out for long enough. So he was able to save about 40 journals from destruction because of my request. But in this paper, lo and behold, let's see if we can find it. I should have looked this up in advance, but he's got lots of formulas, and I don't know how Pittman found this paper. Boy. Okay, so. This is okay. Well, anyway, he uses both rising and falling factorial powers exactly as I wanted him to, and his was this was when I was 1 year old. So, here we go. Well, here's the falling factorial power anyway. Can you you see there's a line under that N there, and we get to the rising ones. What? This one? Yeah. Here's the rising. Okay. So there you are. Okay. So. Now, so at least I can now claim that I'm using Toscano's notation, and it's much better than having to persuade somebody to use my notation, because everybody knows, I put my pants on one leg at a time. That's nice, and I find that with this notation, I'm able to solve problems in a wide variety of different fields, which come my way because of the computer science problems that happen to go. It doesn't mean that everybody has to use it, but anyway, an example of notation that works for me. Now, the one that I want, there were two things that I said, two notes on notation in this paper, and those were two ideas. The first one was also invented by Ken Iverson. Oh, by the way, then he's the guy who, APL language, programming language, that was Ken Iverson's invention. And when he actually got to implementing APL, he changed it, and he didn't use floor and ceiling for that, but he used them as just as a prefix operator. So in APL, you actually just write this instead of the closing bracket. And he also used that same symbol as a binary infix operator for min, and he had max. So anyway, that's he invented the notation, and then everybody started adopting it, and then he improved it in his way. But nobody uses that except to save a keystroke. Now, in this. in this article on notation, I start by actually with a quote from Charles Babbage. Notation was very important to Charles Babbage also, and he had this nice joke. He said that the deism of Leibniz overtook the dotage of Newton. Leibniz was a great inventor of good notations. I mean, when we write an integral sign in f of x dx, that's all Leibniz. But Newton, this d of f of x that I was telling you about, that's Leibniz. But Newton, would write that as y bar, where y is f of x, or y dot. And so we had the, so the deism of Leibniz versus the dotage of Newton, and everybody in England was forced to use dot notation for a long time, held the whole country back for 100 years. I mean, in fact, Babbage was a member of a radical student group in Cambridge that promoted the European notation, and they were starting to use dx all of a sudden in the 1820s. So now in this. Now, the first one I want to talk about is Iverson's nice idea of other nice idea. Wait a minute, where's the tablet? I'm running out of paper to write on. What? Aha, good. Okay. So Iverson had another idea that is very natural in computer work, that he could write x greater than 0 with brackets around it, and that would mean either 0 or 1. 1 if x is positive, and 0 if x is not positive. And he could subtract x less than 0 from this, and this would then be the sign of x. It would be plus 1 if x is positive, 0 if x is 0, and minus 1 if x is negative. And this was on page 11 of Iverson's book on a programming language. So I thought this was, I read this book and I was amused by it, mildly interesting, but informally when I'm solving a problem I started to use it a little bit, and then but then as I started to teach concrete math and started to write this book, it suddenly occurred to me this was amazingly a win in so many problems, that to be able to use this in the midst of formulas. So I'm going to try to explain why in the next minute or so. First of all, the course is about manipulation, how to manipulate, and one of the things we have to definitely deal with is summation, which is the opposite of the delta operation. And so everybody knows, I think, the binomial theorem that 1 plus z to the nth power is equal to the summation of for k equals 0 to n of n choose k times z to the kth power. Same thing actually works, by the way, if you put falling on both sides or rising on both sides. But anyway, that's the binomial theorem. But I learned early on, as I'm having to solve more and more problems on discrete mathematics, that it's much simpler to forget about the limits on this sum. Now, by the way, this summation notation with limits, that was invented by Fourier in the 1820s, and it caused a big, a nice improvement when his notation came out. But instead now I leave out the limits, and I just say it's sum over all k of n choose k times e to the k. The reason is this is 0 if k is negative, and it's 0 if k is bigger than n. So I'm summing over all k, but it's much nicer. I don't have to worry about the limits. The reason is here. I show you get it out of the book here. I'm giving Sean a headache, I'm sure. But you see, take wait a minute here. Okay. This is the one I really wanted. Okay, so you see, you can transform this. You change k everywhere to k plus 1. or you can change k everywhere to, floor of n, 2 minus k, and it's clearly true because as k runs through all integers, so does k plus 1 run through all integers. But if you do it with limits, you've got to do it this way. You see, if you change k to k plus 1, then all of a sudden the lower limit, now you're summing from k equals minus 1 to n minus 1. Okay, so you change k to floor n over 2 minus k, then you got these other limits and so on. So so that's don't worry about summing over a few more zeros. It's not going to hurt you. It's actually going to help you. It saves you a lot of mental energy and avoids worrying about the pattern. And in fact, this formula has another advantage that it works even when n is not a positive integer. It works when n is minus 1. It works when n is 1/2. Okay. In infinite case, we need that z has to be small in order for the series to converge. But anyway, the same formula goes without the limits. So forget limits. That's the first thing. So the next thing is then suppose you wanted to sum over all even values of k, right? So then you actually we have to, on the left-hand side, then we get what is it? 1 plus e to the n minus 1 plus 1 minus e to the n divided by 2, in order to get the even. But anyway, we can do that. But instead, with Iverson's convention, we can actually say n is e to the k, sum over all k, but also then multiply by k even, which is 0 or 1, and we pick up a few more zero terms in there, but that's not. But now we can do all kind of manipulation with this thing on the line here instead of underline, and we know lots of things that are true. Like for example, a and b plus a or b is equal to a plus b. This is whatever conditions a and b are. If a and b are both true, then we get 1 plus 1 on this side, and we get 1 plus 1 on the left-hand side. But if one of them is true and the other one isn't, this checks out. So once we can work algebraically with Iverson's notation and do stuff. I'll give you one more example that's in the book here, showing how change of variables are very natural to do with Iverson notation. So suppose somebody says you want to evaluate over all k greater than or equal to 1, the binomial coefficient of n with the lower index to be the floor of the binary log of k. Okay, this is the log base 2. Okay, so now what we can do is we can say, well, we can sum over all integers m with the Iverson condition that m is equal to, n choose m, but then if m is equal to the log of k, the binary log of k, then we take it 1. If m is not equal to the binary log of k, then it's 0. So this is a way to get that log of k out of the lower index of a binomial coefficient where we don't have any formulas for it in our textbook, and just change it to another integer. But then we make a new condition that integer has to actually equal to the binary log of k. So of course that's correct. But now we've got a double summation. That's not a big deal. We're summing over all values of k, and all integer values of k and m, where m lies between binary log of k and binary log of k lies between m and m plus 1, and k is greater than or equal to 1. And so now manipulating this inequality, we just take 2 to the binary log of k and we get k. So we get 2 to the m less than or equal to k less than or equal to 2 to the m plus 1, and k is greater than or equal to 1. And now it's real easy to sum this on k, because we know how many integers are in this range, and so great. And we get the answer, n choose m, 2 to the n, and we get 3 to the n as the answer. Okay. So now this, I'm not saying there's no other way to solve this problem, but I'm saying that with the Iverson brackets, you start to see how you can do this without thinking, and I think it was Whitehead who said that's the main goal of mathematics, is to be able to do, to solve problems without having to think. Because then we can use we can use our thinking to go to higher problems, but we don't have to worry about this mechanical stuff that we get. Okay, so now everybody knows that Kronecker delta, special case of this notation, which is equal to 1 or 0, depending on whether the two subscripts are equal. Well, this is just a generalization of that. Now. Let's see, how am I doing on time here? Go. 4? What?
408.
408, yeah, that's okay then. So there are many other cases in classical mathematics where people had special cases of Iverson notation. One of them is the so-called Heaviside function, which is this actually just this x greater than 0 function. Well, and a lot of people this unit step function, it's actually x greater than or equals 0 was a Heaviside function, and then people would start putting that inside of integrals and things like this. And in this book here, I tell what I think is an interesting story about this Italian count who's very notorious, Libri. And he got most famous at the end for stealing a huge number of books from France and taking them to Italy and selling them for a fortune. And he also took like Abel's manuscript and various things. So he was first he went to England and started a rare book shop. But he was the librarian for the Academy of the French Academy for a while and so on. But he was, in order to get credibility, he would publish papers, you see, in the academic proceedings, and so he said, look at this interesting function, 0 to the 0 to the x. Now look at the exponent, 0 to the x. The exponent part is it's 0 if x is positive, and it's 1 if x is 0, and it's infinite if x is negative. 0 to the x, okay? It jumps from, So therefore, if you take 0 to that power, it corresponds to Iverson's thing that x is positive. Now, but he didn't have Iverson's notation. But he thought it was really, beautiful that he had a way using notation that was already in mathematics to give this function. And so he started, la fonction. In grand usage, so it's a great. Excuse me, all French people in the audience. But what does this? What does this mean? Actually, I used to know what this means. What? Can you read that for me, Susan?
De cette manière sont très simples et rentrent dans l'algèbre ordinaire. So the formulas that come up in this way are very simple and come into ordinary algebra.
Très simple. Okay. So anyway, so then he would write this formula here. You see, 1 minus 0 to the minus x, and multiply that by something, and that would be the function that would be 0 except 1 if x is between 0 and a. And so he started, so he thought this was great. So anyway, now. But it was why was it important, however, that you had to express that in terms of some ghastly exponent to the exponent, something like that? Why couldn't you just think of another notation that was more direct and say, this is something that idea was a little hard coming, because we're naturally conservative in use of notation, and it's a good idea that we don't abandon conservatism entirely. If every paper used its own notation, we couldn't do anything. So so there's some useful conservative coming in here. But an interesting thing came out in the course of this. There was a debate. Here I say, by the way, some of Lieber's papers are still well remembered, but these are not. I found no mention of them at all in the Science Citation Index. But then one of his other papers led to a series of things by other mathematicians about what about 0 to the 0? And this is still, I'm sorry to say, this battle has still not been won. At least once a month, Mathematica complains to me that 0 to the 0 is undefined, and so you can't evaluate my formula. Now, 0 to the 0 has to be 1, and here on page 22 of this book, this is the most important page from some sense because it tells you why it just has to be 1. But Cauchy had listed 0 to the 0 together with other expressions like 0 over 0 and infinity minus infinity in a table of undefined forms in one of his textbooks that he had at the École Polytechnique. So Libri said. Libri said 0 to 0 is 1, but he wasn't convincing to people. And then a commentator rose to the attack, saying, 0 to the 0 isn't 1, it's undefined. So then Mobius, the guy who had the famous band, and as well as functions and all this stuff, he defended him, and so he said, here's a proof that 0 to the 0 equals 1, and then he went further and he said, in fact, if f and x or g of x are any functions of whatsoever, and x goes to 0 in a positive direction, then you get 1. And then in the next issue, this man S says, well, did you ever hear of the function f of x equal e to the minus 1 over x and g of x equal x, in which case this limit becomes e instead of 1. So if you look now in the library under Mobius, there's a book called Collected Works of August Mobius. His paper mysteriously does not appear in that one, and I have left out a couple of my own papers from this volume as well. Now, anyway, here I'm saying 0 to 0 has to equal 1 because if you want the binomial theorem, x plus y to the n being this sum, to hold for at least one non-negative integer value n, you have to believe that 0 to the 0 equals 1 because you plug in x equals 0 and y equals 1, and you get 0 to the 0 on the right-hand side and you get 1 on the left-hand side. Okay. So anyway, and the number of mappings from the empty set to the empty set is 0 to the 0. And it has to be 1. There we are. Now, that's notation on Iverson's notation. And then I say at the bottom of this page here, if you're a typical hardworking, conscientious mathematician interested in clear exposition and sound reasoning, and I like to include myself as a member of that set, then your experiences with Iverson's convention may well go through several stages, just as mine did. First, I learned about the idea. It certainly seemed straightforward enough. Second, I decided to use it informally. At this stage, it seemed too easy to write just k greater than or equals 0 in brackets. My natural tendency was to write something else in front of it, put a delta in front, make it look a little bit like Kroneker's symbol, or a tau because it stands for truth value. Okay, and similarly, my friend Adriano Garcia, whose 70th birthday we're going to be celebrating soon, decided to write chi, because this is the characteristic function often used to evaluate something to 0 to 1, the member of a set to be. So he used a lot of paper where he writes chi in there. He was one of my professors, and anyway, he said he got the idea from Iverson. But the next stage is that you get tired of writing that because you're using this trick so often that you just all of a sudden the brackets seem right, and that's when Iverson had reached at that point when he first published it. And then after I wrote this article, I got letters from several people pointing out that a wonderful text in probability, maybe 2 volumes by Bruno Di Finetti, made use of Iverson notation, and they, and so they said they used it, and so I commented that, what was the quote I got in one letter? It said something like, according Di Finetti, he says, I am often surprised by new important applications. And I say that remark is so true it evaluates to 2 instead of 1. Now, enough about that. The next part of this, the other notation that developed as I was working on the Concrete Math book was notation for Stirling numbers. Now, Stirling numbers are very important to people who have to deal with both factorial powers and ordinary powers because they convert between the two. So x to the n rising is the summation of n k with brackets on it of x to the k. This converts from rising factorial powers to ordinary factorial powers, and you put a minus sign, appropriate minus signs in there to go the other way. And then there's the other formula which says that x to the n is the summation of Stirling number, which I write in curly braces, of x to the k. This time with a lower factorial power. So now this, if you have a formula and you have to convert into factorial powers, you can use Stirling numbers of one kind to go from ordinary to falling, and Stirling numbers of the other kind to go from falling to the. But so people have rediscovered Stirling numbers over and over again through the history of mathematics, because as they did more and more things with discrete mathematics. But through most of the 19th century and early 20th century, the applications people were working on were continuous, and they didn't need this, and so Stirling numbers would drop out into the background. They never were taught to anybody in school. And it wasn't important because the problems that you were dealing with didn't do it. So they were always being rediscovered every few years by somebody else who needed them. And finally, they were traced back to Stirling. And I found another thing in this book. Actually, I found some manuscripts, unpublished manuscripts of Thomas Harriot from the early 17th century, where he was using Stirling numbers of the first kind in his unpublished notes. So Stirling was, writing in 1720s, 1730s. But since they kept getting rediscovered, there were many different notations for them all the time, and some people would attach plus and minus signs to the numbers too. But the more we started seeing them over and over again in computer science problems, the more we started realizing, if we're going to have, first of all, we like a notation like this instead of s sub n and k or something like this, which because of the analogies, the kind of operations we do with these are rather similar to things we do with binomial coefficients, and so we were able to see how to proceed with formulas like this once we had this notation. But the other thing is that combinatorially it has meaning. So like this brace here, n brace k, is the number of ways to take a set of n elements and break it into k parts, into k non-empty parts. And bracket k is the number of permutations of n elements that have k cycles to them. So there are these natural problems for which we can use this notation not only algebraically but also say, oh yeah, and this means the number of permutations of a certain kind, and then we can see why certain things are true. But still, many other people kept using various notations with s's, with subscripts and superscripts of s's and n's, and I go through a few of them in this as examples, but I don't have time to go. But there was the c sub k of n, gamma sub k of n. Here's oh gosh, there's a zillion ones. Sometimes you use German Gothic Fraktur letters for them, but now the clincher came actually after I had published the first edition of Concrete Math, when all of a sudden I was looking at a paper by Bell Labs researcher named Tex Logan, about Stirling numbers, and he had a formula in there, and I thought I knew Stirling numbers pretty well after having taught classes on them for 25 years, things like this, and he had a formula in there, and I converted it into my notation from his notation, and what his formula said? It was m choose n equal minus n minus m, like that. In other words, the two kinds of Stirling numbers were really the same kind, but just dual it's like this formula of, I said that the negative of the floor is equal to the ceiling of the negative. It's the same kind of a duality. Changing something to its negative changes the, flips one kind of Stirling number to the other. And even the index goes up and down. So, so once I saw this, and then they were all of a piece. Then I knew that things were coming together. I looked back at Stirling's original treatment, and lo and behold, he has a table in his book. Let's see, do I have the same table? Well, I have it in concrete math for sure. So you put the Stirling numbers together in tandem as I did in the second printing of this book. So here's a chart where I have the Stirling numbers here with curly braces, the ones that represent subsets, but then when you get to negative numbers, then you have -5 above and or -5 below and -3 above and things like that. So you get the Stirling numbers of the other kind. -3 over braced with -5 would be the same as a bracket of 5 over 3, and that was this number 35. So when I looked at Stirling's original book, and he gives a table of these numbers, his table actually was the same way. In other words, he had rows of the numbers of this kind. He gave in rows like this, and then but the numbers of the other kind he gave in columns. Like that, because people call this the Stirling numbers, second kind. They usually read up in columns on the this one. Now there was a guy named Nielsen who wrote about Stirling numbers and traced it back to Stirling. I think it was actually the early part of the 20th century, and he it was in Germany. Talked about the numbers of Stirling of the erster Art and zweiter Art, the first kind and second kind, and that's kind of dumb. I mean, if you're going to talk about, it's not mnemonic. There's no reason to what if we had said plus is addition of the first kind and minus is addition of the second kind? Wouldn't we we have to remember which was which, right? I mean, so instead, it's much better to say, oh, these are Stirling numbers that refer to permutation cycles, or these are Stirling numbers that refer to subsets. And besides, it turned out that the numbers that Stirling considered first in his paper were the ones of the second kind, according to Nielsen. Well, anyway, so that was a dumb notation. This still survives because so many people, have read the older literature and been trained that way. Now, so once we had this notation, then lots of other formulas started to click, and it was working not only when m and n are integers, but also when they're complex numbers, and working in general. So I give in this paper a whole bunch of examples of formulas that that naturally hold. Then once we have the right notation for Stirling numbers, here, for example, is the generalization of the formula for converting ordinary powers to falling factorial powers. And this works whenever z is a complex number with positive real part, and whenever alpha is a complex number. So, and the corresponding ones for going the other direction also are either true as equalities or as asymptotic series. And this means that a lot of problems that we used to find rather difficult we would work through from Stirling numbers to other things, and then we'd go through a whole bunch of manipulations, and then we'd get back to another answer. Now we can work directly with Stirling numbers and get the answers directly and get further. So this is why I thought the notation for Stirling numbers using braces and brackets was a big win over the other notations I had seen. Now, one of the greatest surprises I ever had in my life was After I published this paper, I got a letter from my friend Philippe Flageolet in Paris, sending me a Xerox copy of an article that he said was by, let's see, is he no, he's a Romanian. Let's see, Karamata. Karamata, somewhere in what used to be Yugoslavia, anyway, published in 1932, Belgrade. Okay, so he's Croatian. Okay, so he, in this paper in 1932, that I had a Xerox of from Flageolet. Here's a paper by Karamata, and he says, let's use these notations for Stirling numbers. Susan, cette notation la forma in other words, because by this notation the formulas become more symmetrical. Okay, and so I thought this was too good to be true. It had to be a hoax. So I went, he's doctored the Xerox copy. So I went to the math library, and sure enough, it was, I could find this journal, and sure enough, it was there. And so last year was my, the big moment in a computer scientist's life is when you reach your 64th birthday. Because then you're 1 million in binary, you see. So this, I'm not gonna reach 2 to the 7th. So we had a shindig here, and Philippe came, and he presented me with this treasure. It's one of the greatest things in my collection, and this is a reprint that I'm not allowing anybody to take away. You can have any of these reprints on the floor here, but this is actually taken from this journal called Mathematica, of all things, volume 9 by Karamata, and you open it up, and sure enough, you've got the notations for Stirling numbers. And he said, by this notation, the formulas become more symmetrical. Okay, so there it is, and he proceeds to use them exactly as he could have swapped the braces and the brackets. He could have put something in up, but he had exactly the same intuition. So this was one of the huge happinesses for me to have this, and the only thing I forgot to ask Philippe to sign it. But he had actually he'd been browsing on the left bank in Paris where there's bookshops, and just happened to run across this preprint, according to him. And so that's why I say, if you pick up some of these preprints here now, you never know, how somebody you'll make happy someday, right? So is Lyle here? No. Lyle said, great. Yeah, I had an email from Lyle saying that he might come. But anyway, I want to talk a little bit about a notation that Lyle Ramshaw and Tony Hoare independently invented, because it's another one that I think is good, but and so I've decided I'm using it in my books now. But it's much more so far in the computer science community than in the mathematical world, and that is this notation which we find here for intervals. Now the thing is, once we start using commas and brackets, then we start running out of different notations. And for people who start working in several fields of mathematics, everybody, so in all the calculus textbooks now, and I don't know, this will probably go on for a long time, but people write, 0, 1 for the set of all real numbers between 0 and 1. And in concrete math, however, I'm now writing according to Ramshaw's notation, 0.1. It's a notation that hasn't been used for any other purpose. And a lot of programming languages use a colon for a range of, in Pascal we used to do this in order to say that you had an array whose subscripts ran from 1 to n. We would say 1.n. And similarly, if you put a parenthesis on one side and a close on the other, this means that you leave off 0, but it's all numbers that are greater than 0 and less than or equal to 1. And there's 4 possibilities. So that's a notation that I think deserves to be more widespread, but it's not holding many people back. But if you write A, comma B, this means an open interval of all things between A and B, but it also to a lot of people means the greatest common divisor of A and B. And for others people it means point AB in the Cartesian plane, and so on. It's an ordered pair, and so in my books I found it was better for pattern recognition when it's an interval to use these double dots here, and very easy to typeset with TeX. I have DTS for 2 dots and DOTS for 3 dots, actually, when I went. And for 4 dots, well, I haven't come across. I came across 4 dots once, actually. It was talking to John Conway, and we were talking about extremely large numbers, which are so huge that that the human mind can't comprehend them. Some numbers are way bigger than Ackermann's function, and so when you write 1, 2, ... n, where n is allowed to be as large as these incomprehensible numbers, John suggested that we maybe use 4 dots for that. But anyway, I do. So when I made this book, I went through all these papers that I wrote, and I updated the notations to so that it's consistent with all the papers and with all my other books. And I didn't have to change too many things, but the intervals I had to change more often, because this was something I learned about much later in life. But now I hope I found every place where I had an interval in the original paper. Okay. Let's see. That's about all I wanted to get off of this page. Oh, no, there is another one. That's another one that actually, what about the one that's the greatest common divisor? I decided I was going to write GCD in front for the greatest common divisor and least common multiple and things like that, because I wasn't writing a book on number theory, and it didn't hurt me to write GCD about 20 times in my whole book. But if I had to write it 20 times on every page, I would be quite happy to leave that out. And in fact, that goes for every kind of notation. Whatever problem you're working on, you don't have to use an awkward notation just because it conflicts with something that you did last year. Whatever you're working on now, you can have a local notation for that purpose. But if you're making only occasional use of something, then it's important to have consistency across your paper, so that you don't have to you don't have to define notation over and over again every time you use something. You can say like we do here on one page, this is what we do. But very often I need the case. I need what number theorists always write in long term: A, B equal 1, which means that the greatest common divisor of A and B is 1, which means that the numbers are what we say is relatively prime to each other. They don't have any prime factors in common with each other, and so this kind of notation occurs over and over again. And so number theorists began about 15-20 years ago. A lot of number theorists began using a new notation for this, namely that A is perpendicular to B. The two numbers have no prime factors in common. Mean it's very analogous to being perpendicular in the sense that if you look at the dot product of their prime exponents, is 0. The vector product is 0. So that's perpendicular. So in concrete math, I have this plea for this notation to go and become widespread. So where did I put this here? Page 115. Okay, it would have taken a while to get to it. Relative primality here. Okay, this is a quote from Concrete Math Book. When the greatest common divisor is 1, we say they're relatively prime. The concept is so important we ought to have a special notation for it, but alas, number theorists haven't agreed on a very good one yet. Therefore we cry, hear us, O mathematicians of the world. Let us not wait any longer. We can make many more formulas clear by adopting a new notation now. Let us agree to write m perpendicular to n and to say m is prime to n if m and n are relatively prime. In other words, we declare this to be true. Okay. So, actually, I think when I wrote this, before I had discovered a bunch of number theorists using the notation, probably found that out a couple of years later. But anyway, that's what occasionally I get to the point where I say, here's notation shouldn't be too changing too fast, but every once in a while we get to a time when it's time to that it's time to say, well, let's go with this one. It seems to be working. Now, not every innovation that I've proposed has been a winner. The ones I've been talking about so far are ones that I strongly believe are still on the ascendancy, and I wouldn't be surprised if they were common usage, 100 years from now, because to me they're so obviously good. But there are lots of other experimental things and things that I thought were good at one time, and then I changed my mind. I'll talk about a few of those next. But in general, notation, I don't ever claim that I could prove to somebody that a notation is better. It's a matter of taste, and there's no arguing over taste. I was just looking at Edsger Dijkstra's. I have a CD that has all of his 1300 documents called EWD1 through EWD 1300, and it's all in PDF format now. And I start, and he had 3 or 4 of them on notation, and I was looking at those earlier this week. And so, he has very strong opinions about things, and he had some good notations in there, and others that I thought stunk. And I'm sure he would say the same about mine. And it's a matter of taste. And in fact, he himself said that the more important thing was not to adopt the taste of your. The most important thing for a professor is not to teach the students what their taste ought to be, but he should teach the student, or professor should teach the students the importance of having their own taste, and so he wouldn't insist that I adopt all of his notations either. But he tries to, we both try to put things in the best light that we can. And the next chapter in here, in fact, is about an experimental notation, which I still like, but it hasn't swept the world, so it might very well be not too good. In special cases, we know it's pretty good. Namely, here's a notation that I use over and over again in zillions of works, and it was invented by I think Goulden and Jackson about 25 years ago. You put in brackets in front of a power series, bracket z to the n, and then the power series, some generating function, some function that's the sum of powers of z with coefficients, and this extracts out the coefficient of the nth power. And Goulden and Jackson here. And now, Goulden and Jackson also said, however, if you use the notation z to the n in brackets divided by n factorial, and then you give a generating function, then what he means is it's the coefficient of z to the n over n factorial. So it means that if, for example, n is 5, it's the coefficient of z to the 5th over 120. And so you take the coefficient of z to the 5th and you multiply it by 120 in order to get what they did here. Now, I found that this was not leading to anything useful in the times I was trying to use it. It was only leading to confusion. And so instead, I decided, wouldn't it be nice to make this a linear function where you could put any 2 generating functions together, and you would extract out the f part of g. And so, for example, z squared plus 2z cubed extraction of g would say that you take the coefficient of z squared and you add twice the coefficient of z cubed to that. And well, it turns out to be, an associative operator and things like this. And so I discussed in this chapter bracket notation for the coefficient of operator. I discussed about 10 different problems, which I think are solved nicely by this notation. But until somebody else decides that it's a good notation, the beauty might only be in the eye of the beholder here. So this is an example of an experimental notation where I did is, the one that seems to be actually maybe the most of a win is just when you even just reduce it to the case where the thing in brackets is only 1. So I discuss here. I give I think the shortest ever proof of Lagrange's inversion formula here on page 54, using this notation. The idea of the proof isn't mine. It's due to Peter Paula in Linz, Austria. But it works so beautifully to do it. So anyway, those of you who are interested in that kind of thing might be interested in chapter 3 of this book, and I give try to track down the history of the thing. I've been talking a lot. Are there questions? Yeah.
Talking about notation, this has been in my mind for about maybe 30 years. I wanted to ask you. Talking about notation, I mean, programming languages are also notation.
Yes.
What's your favorite programming language?
What is my favorite programming language? That's book number 5 in this series. So, can you come to the Computer History Museum on December 3rd? No. But the answer is complicated, but right now, I write in C-Web almost all the time. So, I'll write 5 C-Web programs a week, which is a combination of English and C. But depends on what I'm doing. So, and many times in my life, my favorite programming language was the one that had the best debugger. And it didn't matter what the notation was. It was more that I could get the bugs out of my program. And I could live with any stupid notation as long as I had some control over figuring out why it was blowing up. I enjoy lots of different programming languages. They keep changing all the time, and so I've been very conservative in that respect. That I don't learn a new language every time it comes out. And in the Fun and Games volume, I'm going to have a chapter about the worst programming language ever invented. It's called Intercal, and it's hilarious. And if you want to know more about it, look it up on the web. Okay. Yes.
Do you have any thoughts as to why it would appear that infix notation in programs is more popular than postfix or prefix notations?
The question is the insight as to why infix notation is more popular than postfix or prefix notation. So prefix notation would be like plus of x, y, z to stand for x plus y plus z, right? And postfix notation would put the operator on the right-hand side. And it's actually the verb in German comes last, and I mean sometimes this goes into national the mentalities that are drummed into us when we're in school as to what we go on. To me, it's more for the kind of things I'm talking about today, doing mathematical problems rather than expressing to a computer. The important thing is what's easiest for me to see patterns, because I've got a one-dimensional structure, a bunch of symbols, a little bit of two-dimensional, so you can have fractions. And I have to be able to perceive patterns, and so by putting by putting the operator in the middle, that helps me visualize things better than if it's off to the sides. I'll often, somebody says min of x and y. Here, take min of x and y, right? And then you have max, and then the max of the min of x and y with z. Okay. Now, but another notation is x min with y like this, and then you take, and then the max with z. And then you have a distributive law that this is x, this happens to be equal to the min of x max with z and y max with z. And when you write it with an infix operator, it's much easier to see its distributive law. I mean, that's why I think infix go. Now, by the way, one of the things Dijkstra said is he hated. He would never write a paper that had 3 dots in. Here I got 4 dots, but he would never write a paper with 3 dots in. He thought that was being sloppy. You wanted to have instead some kind of a, some kind of a logical notation for an interval, interval here. So he would never write x1 through xn, but he would say x sub j, and then he would give some kind of qualifier, for all j in 1n or something like this. I see patterns when I write it with dot, dot, dot. I can sort of see. That's why I put 4 dots in the first place, because that makes me think big, It makes me think this is big. I can see this stuff is all sitting there, and I can imagine what the formula was for when the dots are missing. And he's maybe very good at imagining what these quantifiers mean. But to me, I wanted to see what the numbers were, as if I could think of what those guys were. That's why that notation. That's why I disagree. In fact, I wrote one of the preprints that you find here is called a generalization of Dijkstra's algorithm, and Dijkstra has a famous algorithm for shortest paths in a network, and I generalized it to context-free grammars, so it gives you the shortest string in a context-free language, and a path in a graph is the set of all paths in a graph is a special case of a context-free language called a regular language, and so I generalized that to context-free languages, and I have lots and lots of dots in that, and so Edgar wrote me afterwards, said, well, Don, it was a nice idea, but why didn't you write it without dots anywhere? So he never liked dots. Percy?
You've had a lot of great successes with notation, but you've also had some spectacular failures. I wonder what your favorite was. Mine is perm. You try to get people to replace permutation by perm, and
okay, yeah, okay.
Painful.
This is. So I let's see. Is that in? No, that's in the. It's in the volume on analysis of algorithms. So okay. So this was to be equal to permutation. You see, I figured. In fact, Von Pratt suggested this to me, but he now denies it. But I figured, I'm going to be using this word permutation so many times in my life. I would be saving 1,000,000 syllables if I started calling it perm instead. And some people, of course, call it a permutation, but that's another joke. In fact, I found out that. As I said, all these lectures are now going to be on the internet so that anybody can watch them anytime they want to. And a couple of weekends ago, I watched all 10 or 11 that were ready at the time. And I realized that in the future, I'm going to have to stop telling the same jokes over and over again. It gets kind of tiresome, I think. But so I can't use any of these anymore. But so the idea was, we just save ourselves millions of syllables in future research, and we call them perms, and so we had a perm group and all this. It grates on the ear.
What's your
in that same paper?
The worst notation.
Yeah. Okay. Now notation also, there's this word bag, by the way, which I hate for the same reason that I came to dislike perm, because it just sounds too much like a bag lid. I mean, it just sounds too gross instead of multi-set. So multi-set is like a set, but it has repeated elements, and some people seem to, I think even Dijkstra, seem to think that this was good. Of course, in Dutch it might sound very good, but no, that doesn't work. Okay, but in this, so you want me to give an example of some of the real losers? Well, you know, I tend to suppress these. Okay, well, I had notations for shifting left and shifting right. Now, so right now in C, we X A left 5 means shift A left 5 bits, or 5 binary places, and similarly for right shift. And I had a bunch of things like that I was trying. Like this one, I was going to have this symbol, but anyway, this one seems to be winning now. Then I had notations like 5:A to mean the first 5 letters of A if A is a string, and A:5, for the last 5 letters and things like that. And it had some interesting properties that 3:A:5 if A is sufficiently long. This is meaningful. You could parenthesize it either way, and it would still work out. But it's similarly, I could say A like this is A. Chop off the first 5 letters of A. And when you're dealing with strings, you need some kind of notation for strings. So I played around with things like this, and they are more or less awful after, but sometimes they work, and I've not tried to promulgate things very often that I haven't experimented with. This perm was an exception, but in that paper, the same paper, I have another notation that I still believe is very important, and that is to write instead of x to the -1, I write x to the minus. Now, I'm not denying that you could write x to the -1. That just happens to be x to the minus raised to the first power. I mean, it's just, it just saves. It just saves me writing this. Now this might seem funny to you guys, but when you're doing group theory, you're writing -1s over and over again. And so whenever I'm working on group theory, see, these are elements of the group, and I say, what's the inverse of alpha beta? I'd say that's beta inverse alpha inverse, and I'm getting way ahead there, and I'm very confident about that being a useful notation. And if people don't like it, they can always write the 1s. It doesn't bother me a bit. Yeah.
You remove the limits from the summation. Why not you remove the summation altogether? And
Excuse me, I can't hear.
You remove the summation in your.
I removed the summation.
I mean the limits of the summation.
The limits of summation, yeah.
Why not remove the summation sign altogether, and rely on?
This is what Einstein did, and it really confused me. He said every time you have a formula that has 2 x's in it, that means you were supposed to sum over it and things like this. And boy, I need something in there to tell me that I should apply my sigma type pattern recognition. The purpose of notation is not to minimize the number of strokes. Here I said, okay, I didn't want to find myself writing 1s all the time, but it was mostly that I can, okay, I'm saving myself a little bit, but there's mostly that I'm able to see patterns. If it's short, so much the better. But sometimes it can be so short you can't figure it out at all. A programming language I used once was called IMP. It never got popular, but I used it. It was invented by Ned Irons, and we used it in Princeton in the 60s, and it was extremely terse language. Instead of saying, if x greater than 0, then in IMP you wrote x plus implies, or something like this. Very small keystrokes. You could type your imp program real fast, and they'd only be a few lines long. But if you tried to read them again the next week, you couldn't figure out what it was. So sometimes verbosity is helpful.
I have a question. It's not about notation. It's about typefaces. In the old-style numerals that you have, in which the
Old-style numerals, okay. Yeah.
In the old fonts, the one doesn't have a slanting stroke, but a horizontal stroke on the top. Why did you choose to put the slanting stroke on the one?
Because this looks like an I to Americans. And Hermannshoff agreed with me. The question was, why did, in the old-style numerals, the Encyclopedia Britannica has mathematic formulas in which it goes 1, 2, 3. But in my book, I have old-style numerals, and the 1 has only one stroke on it. It doesn't look like that. And this was something that was in books, but it always, to me, it looked too much like the letter I. And this was sufficiently, it's a small I, and maybe it would confuse somebody from Turkey, though, because they're very sensitive about the way I's look in Turkey. Okay, thanks very much. Help yourself to these